Hi everybody, welcome to our stream this evening. We are trying YouTube again. I want to thank everybody for your patience last time and coming all the way back to Facebook to make sure you got the information. I'm really happy you did. If you are on Facebook, there is an event there. You're welcome to post things in. I'm going to watch that discussion. I'll also watch for messages from anybody if they need to send them to me. And I'll also watch the live event chat here on YouTube. Now, I probably, let me see if I can do this in a separate tab. Yep, sorry. So, I see that Brady's there, Chris Young is there. Hello, how are you guys? And so I will look there for the primary chat here tonight, which is different for me, so bear with me. But I will watch there, and I hope we get something accomplished out of tonight. So my goal here tonight is pretty simple. I want to show how to make a PCB, with a AT slant, something that's useful for the world of AT, but also to kind of show you the end-to-end process of how to make a PCB in general. We're going to use Eagle. I do recognize there are other options. KiCad, however you say that, is certainly one. You can also use fritzing if you want to use that. I use that for other things. I'll also warn you, I've been dealing with a sore throat. I choked on something last night and I've got a scratch in my throat. So if you hear me turning off the mic, it's just me coughing, and if I forget to turn it back on, please yell at me. Chris, I'm glad I'm coming in fine. That's wonderful. So let's talk a little bit about what we're going to try and make tonight. So we're going to try and make a switch isolator. It is not that important what it is that we're talking about. It is much more important that we talk about the process and why this is useful. So I'm going to go ahead and show an overhead. Not that overhead. All right. So let's move this. All right. So this is kind of the device we're going to talk about making. The device right here is a switch isolator. I made this years ago, and I recommended it to a couple different AT vendors that they sell it. It is sorry, my phone is exploding, which is awesome, but not helpful at the moment. So we wanted to be able to use something like the candy corn to control something that had a motor. And in fact, specifically, it was a 12-volt bubble blower. And it didn't work. And the reason it doesn't work is that this device does not have a real switch in it. It does not have a reed switch or an actual physical switch. It has what's called a Darlington pair in it. It has basically a switch that's solid state, that's transistor based. It's not really a physical switch. And when you're trying to switch something like a 12-volt motor, sometimes it's not going to be able to handle the current or handle the inductive load to make that happen. So I created a little device so this switch here plugs into the isolator, and all it really does is that when the switch closes, it closes this relay. And when this relay closes, it controls whatever the toy or device is that you're trying to control that needs to have a physical switch, okay? In this case, it's controlling a fart gun because I figured I wouldn't have to use up any space on the video and you'd know when it went off. In reality, the candy corn can control a fart gun just fine, but this is as good as any as I can show you. So in this case, I'll show you kind of how I made this. You know, things are soldered together with wires. I just used a piece of perf board. I'm going to walk you through what the components on this are, but really quickly, there's two jacks, two stereo jacks. There's a relay, a transistor, a resistor, and in reality, there should be a diode, but there's not. And then there's a battery switch, a battery case over here, right? So there's a battery that drives this thing. And when I made this, I expected people to say, oh, this is a good idea, we'll make one of these, or this should be an add-on. It's not a complaint about the candy corn. This is simply not meant to control that kind of current, right? That's not what that device was made for. But it is something that especially when you're first starting out with a switch, you might want a motorized train, a 12 volt toy, lots of things that the candy corn might not be able to switch. What I got instead was, well, that's not going to get anywhere because it looks like it was homemade. And specifically, actually, I had it inside of this. Sorry, we have to turn that off. I had it inside of this Altoids tin, and the comment from the AT vendor was, "You're not going to get anywhere with that thing in an Altoids tin." I'm like, well, the point isn't to sell it in an Altoids tin, right? It's to make something that's useful. But this is kind of a perfect example of where a PCB might be handy. With a printed circuit board, we can make this about half the size, and we can have it with no wires. So there's nothing to break. I'll tell you that when I got this out today to show this example, I had to rewire 2 of the wires because they had just broken off. It had been a couple years, but still, it's not a good long-term way to make things. All right, so enough about this. Let's talk about what the components are on it, and then we'll talk about how to actually make the PCB. Okay? By the way, there's questions. Ask them in the YouTube chat. I will occasionally pop over to Facebook to watch for comments, but I am going to watch the live chat, the chat section of. I'm going to use all of it. Live chat. There you go. The chat section for any comments. Feel free to interrupt me. And a big disclaimer here. I'm not a PCB expert. I'm not even a hardware expert, right? So I spent the last 25 years writing software after getting an engineering degree from the University of Florida. I took circuits and solid state and microcontrollers in a previous life. Everything that I'm going to show you today, I've learned in the last year by watching videos, just like you guys are. Brady asks, can we use a 3032 battery like in the candy corn? No. That is directly from Lemoore. You cannot use that. It does not have enough current to source the current needed to flip over the relay. So Brady's asking about using a coin cell. That will not be enough. A AAA battery is enough, which is what we're going to use for this one today. All right. So what are the components in this thing? First things first. There is a couple of resistors in our design. There's only one in the one you just saw. There's a diode. This is just for protection, and really, in all honesty, this is not needed. There are reasons for putting a diode in. It's a really good practice to do, and we're going to do it. But in this particular use case, it really isn't necessary. We have a transistor, which is a little gate device, a 3-prong gate device, and a relay. Finally, a battery holder. So these are the parts we're going to put together. We're going to try to put them together into something useful. Probably the most interesting device here. I mean, this doesn't let current through. This only lets current go through one way. This acts as a gating device, and this provides power. This one is actually worth talking about, a relay. It is a motorized switch. That is the best way for you to think of it. And I happen to have a clear relay, so I always like walking through this if I can. It's really kind of cool. So if you send current between the 2 terminals of the coil here, what happens is this electromagnet right here will turn on, and it will pull this little piece of metal up against that one. Okay? If you look carefully right now, these 2 terminals, these 2 spots are being connected. So if you look, this pin goes up, is connected through this post to the white wire and out. And then when the current goes on in the coil, it actually pulls this metal over. So it will pull this pad over. So then this terminal will go up through the white wire and out. And so it literally is a motorized switch. So this terminal is called normally connected. This one is called normally open, and this one is called common. Okay, so generally this is the current going in, and then it will either go out this one or this one, depending on whether the current is going through the coil and whether the relay is on. Okay, so all of this is basic circuits, and to be honest, most of the people who want to make PCB boards already know everything I just talked about. It's mainly for the people who are here just for just for the fun. But let's go ahead and talk about how we lay these out in a PCB. Okay. Any questions on that or not? By the way, I'm going to cheat a couple times here tonight. I'll tell you when I do, but I am going to cheat a little bit. I have gone ahead and done this project because I'm not completely crazy, and so I will occasionally double check over to another version of Eagle because I don't want to get it wrong. Okay, all right. So we are going to use something called Autodesk Eagle. Eagle is a piece of software made by EagleSoft, which got bought by Autodesk a few years ago. It is not free. It is ridiculously expensive, or at least it is very expensive. But it is free for people like us. So it's free for folks who are using this as a hobbyist, as a startup. If you're making under 100 grand a year on your business, if you have, it is very progressive. They want to charge big companies a lot of money and little companies a little bit of money. Whether that's good in the long run for their business is up to them. They're certainly welcome, and I appreciate it. These are really, really good electronics CAD tools, okay, computer-aided design tools. So we're going to first start by creating a schematic. It's going to end up looking like this when we're done. I hope you guys can see that. I'm not sure if you can. Yeah, you can. Okay. It's going to look like this when we're done, but I will go ahead and walk you through how we do it in Eagle, and I will just refer to the part numbers so that I get them right. That's really the only thing I really cheated on was I did look up all the part numbers beforehand so that I can do this. Okay? Let me make it so I can see your chat again. All right. All right, so we're going to make a circuit. Let me see if I can bring up yeah, I can. Hold on a second. Let's see. Oh, hello, Lucas. So this is the thing we talked about before. This is the basic circuit that we talked about, and this was before I put it together in real life. There is a post on the Facebook group if you want to go back and look at why we did this and when we did this. But I'm just going to replicate this inside of Eagle. Okay. So the first thing here is I'm in the schematic view. You always start out in the schematic view. You get to building the board later. You have to have a working schematic, or at least a basic schematic, before you can start. So let's talk about what we're going to want to add, and that's exactly the tool we're going to use is add. It's over here on the left. I almost never try to find the tools in this toolbar. You can just start typing. And if I type in ADD, sorry. If I type in ADD right here, it will actually change this tool to be the add tool. Okay? So it now pops open the add window where I can choose from like millions of parts. And they're all in here. What I'm going to do is I'm going to look for a battery holder. So star, battery, star. I happen to know that the one I want is Adafruit's AAA battery holder. And I'm going to hit OK. And you'll see that in this design, it is shown just as a voltage source, just as a normal battery source. I'm going to flip it like this. And I only need one of them, so I'm going to hit escape. And there's my first component, okay? So this thing actually has a couple different places where I can put wires. Let's go ahead and get all our components on the page first. The first thing this thing needs to go to is it needs to go to our switch. We're not going to put a switch in here, but we are going to put in here, we're going to put in here a stereo, stereo jack. And there's a stereo jack. We're going to hit OK. So you'll see how here it's got a bunch of different terminals. We're going to talk about the different values of them in a minute. I'm actually going to need two of these, one for the input, and we'll put this one down here, one for the output. Okay. The other things I'll need is I'll need a NPN transistor. I happen to know that that's whoops. That is a 2N222 transistor, and that's going to go right here in the middle. And then I'm going to need a couple of resistors. Now, you're going to get tons and tons and tons of resistors. The size I'm going to use a 030910. This is a standard through-hole size, and with 10 mil or spacing. I need one here. I need another one here. And what else do I need? I need a diode. So I need a diode. And we'll use the IN 4004. And that goes over here. Whoops. And I'm going to need a relay. Now, in this case, I'm going to need TX2 size relay right here. And come on. Oh, sorry, I got to pick one. TX2, 1 volt, 1.5 volt, and it's going to go right here. All right. Now, these are the components that we're going to need to make this board. Hopefully, I'm not losing anybody. Here, explain to the audience how you are orienting or rotating this part. Sorry, good point. So as I'm moving things around, it's kind of second habit. Thank you, Chris, for telling me that. So let me go ahead and move. So when it's on OBS and I type any letters, it changes the screen. So sorry. If I'm moving a component like this one, so I click to pick it up. I'm not holding a mouse down or anything here. If I want to rotate it, right, I right click and it rotates it. So I can rotate it just like that. And I'll just put it back here for now. If you're on the, in a minute when you're on the board, that also works. It'll rotate things. If you want to put them on the front and the back, you use the middle click. We'll get to that as well. All right, so let's start to wire this up. The scroll bar moves in and out, so if you see me doing that, that's all that is, okay? Let's take a look real quick at the stereo jacks. These have a couple different terminal points, and I'll show you a good little trick. So you can look at this schematic and kind of figure out, all right, this is the ring, or this is the sleeve, this is the ring, and this is the tip, because if you put a plug in from the right-hand side, that would make some sense. Excuse me. But if you don't want to trust their drawing skills or things like that, you can actually right-click and say breakout pins. And I'm going to select the pins, and it's actually going to show me these different pins. Oh. So the one that I chose from Adafruit actually doesn't have the names of the pins. I'm going to go really quickly. Let's show you a good tool. I'm going to replace this with the one from SparkFun. So I'm going to hit replace. And in this case, I'm going to go Star Audio. Just because the one from SparkFun does a better job of breaking out the pins. I'll show you why. All right, SparkFun 3.5 millimeter jack. Okay, so this is basically the same look. Okay. And so this is the new jack. Did it do it? I don't know if it did. No. All right, so let's just delete these. DEL. Because I do want to show you breaking out the pins. It's really handy. And let's add these again. So we're going to add these audio jacks right here and here. Okay. And what's nice about these is that now when I hit breakout pins, they've actually named the pins. Okay. So in my case, I know that I want to use the tip, the sleeve, and the ring. And these other two are ring and tip connected. It's a way for you to know whether or not there is a jack in the, whether or not there is a plug in the jack. Without actually having current flow through it, it's just a way for you to detect whether or not there's any current going through there. So we'll add those pins, and you'll see it now gives me the tip, the ring, and the sleeve right here. Okay, and these are pulled out. Okay, so you'll also see it, for some reason it puts the name right on top of everything else. We'll clean it up later. It's unimportant. We'll do the same thing down here on the other jack, and I want ring, tip, and sleeve. Okay, so this is all good. We can now access these. We know which is which. We're not going to get them wrong. Okay, I hope that helps, and thank you, Chris, for reminding me to let people know. So let's go ahead and start wiring things up. Now that we've got these, so to wire things up, you type in the net command. It's for creating networks of current and networks of voltages. And then you just start wiring. So in this case, we want current from the battery to go into the tip of the jack, the input jack, J1. Okay. We want current to come out of the sleeve, and we want it to go into this resistor. Okay. In reality, we also want to connect the ring and the sleeve. Okay. We're going to call it sleeve when it's done. The reason for doing that is that we want this to act like a mono jack, just like we do whenever we're doing AT stuff. We always want to work in terms of mono. So that just gets rid of the confusion around, what happens if it doesn't go all the way in, things like that. We're going to connect this resistor to this transistor. So when current goes from the battery through our jack, through our switch, and back to this resistor, it will then go into the transistor to allow current to flow through it. Hopefully that makes sense to folks. As far as what happens next, let's move our the coil for our relay over here. Okay, and we'll run a wire here that says, all right, I'm starting from my battery voltage, I'm going into my coil, I come out of the coil into my transistor, and I come out of the transistor into this resistor, and then back to my battery. Okay, in theory, to be honest, that's the vast majority of this circuit. Okay. Ignoring the stuff on the right for a second, when your battery's on, it's going to send current out through this jack to your switch, which sends it back. That turns on this this gate on your transistor and allows this current to go through the coil. As I showed on the relay earlier, when current goes through that coil, it's going to make these switches, the other part of the relay, turn on. Okay, so let's go ahead and move some things over here. You'll see there's actually two K1 switches. There's this one and this one. Whoops. We are only going to use one of them. Almost all relays are double pole, double throw, which means they throw two switches at a time, including that clear one that I showed you. But we're only using one in this case. And there are cases where we use two. But just to clean up our design here, I'm going to go ahead and delete this one. Okay. And I'm going to move the diode up here. And we're going to talk about this diode for a minute. So I hope there are no questions. I don't see any questions in the comments section. I hope you guys are getting something out of this. So this diode is here. It is a flyback diode, and it's really not needed in this particular circuit, but it's a really good habit to get into. Whenever you have a motor or a relay, there's a chance of it hurting your circuit. Specifically, if you're using a microcontroller, if you're driving it from a pin from your microcontroller, what can happen is the current goes through the coil. And while that is held open, it builds up a magnetic flux and builds up a magnetic flow. When you turn it off, it can create current in the wrong direction. It can backflow. It's called flyback. It's a 1.5 volt battery. There is no microcontroller. We don't need this diode, but it's a really good habit, so we're going to add it. So what you do is you add a diode that basically runs from the, let's see, net. It runs from the negative side of the coil backwards. So if you think about what this really means, when this is turned on, no current is going to run through this diode. It's going backwards, right? If there ever is a high voltage here, because your transistor is turned off and the magnetic current has induced some voltage here, it will fly back up to the battery safely, rather than heading this way and hurting this circuitry right here. This is not critical, but it is a good idea. So it's in there. And the last thing we have to do is we have to attach the second jack. So let's move this stuff. So when you want to move multiple things, there's this little selection thing. It's called group. Basically just lets you move stuff together. Okay? And we basically want to wire the, so we want to, again, wire ring and sleeve together and call it sleeve. And then we want to put the sleeve on the, let's put it on the common side of the relay. And we will put the tip on the, I can't see, sorry. There's a little circle right here. I'm just trying to get it to light up. There it is. Okay? So that is connected to that. So when this coil goes on, this will flip over and make our jack turn on. Okay? So hopefully that's not too complicated. If you've got questions, let me know. Brady says that somebody told him that the dice spinner needed a relay. Maybe. This is certainly a good use for it. You can incorporate a, you mean a flywheel. Gotcha. A flyback diode. It might. Yeah, it's got a motor with nothing else, and if you're connecting it to something like a microcontroller, yeah, you'll want to have some protection on there. So, but this is your basic circuit. Let me zoom in here and make sure you guys can see this. And so I'm going to go ahead and save this as, let's see, save as a live demo. Why not? Okay. There's a lot of things I could do to clean this up, like, you know, adding any comments on it or a name or things like that. You can actually clean up these, where the text is on top of each other. Some of the things you'd use to do that are odd, like the word smash. Smashes a component into its different parts. I will leave that for an exercise later. Both Lamore Freed, Lady Ada has great demos on this. Eagle, Autodesk, which makes Eagle, has great videos for doing this. So let's just say this one is good enough for right now so that we can talk about the PCB part of it, okay? Once you've got your diagram fairly correct, and by the way, if anybody sees a problem with this before we get going, now's the time to tell me. Do you need a connection for the relay to trigger it? That's a good question. The answer is no. So the relay is shown here in two parts, okay? And one thing I can do to make this a little bit easier is I can make a line on the info. So all the layers are right here, and I'm just going to make this an information line. So I'll put it on info. It's not going to carry any current. And I'll make it dotted. But if you look from, if I can make a line from here to kind of show that these two things are related, okay? This is one part of the relay. It's the coil. This is the other part of the relay. It is the switch. And maybe it's worth going over here back to the overhead for a second to explain this. Maybe if you look at it from this angle. So these are the 2 points of the coil. And then these are the common normally open and normally closed connections for the two parts, okay? So on my schematic, this round electromagnet is one component, and this switch is the other component. The fact that they are that they're separated is convenient, but it is good to have some kind of an indicator that that they are related. So I added that note, but that doesn't actually change the the circuit at all. It just makes it easier to read. Okay. So this line kind of hopefully makes that clear that they're related. There might be a standard way that you're supposed to represent these. If anybody knows it or has a better idea, type it in the comments or make a comment later. Okay. All right. Excuse me. So let's go ahead and make a PCB. So we've got our entire circuit here. Let's go ahead and see what we can do. So if you go up to File and go Switch to Board, it's going to say there is no board file. Do you want me to create it from the schematic? And we're going to say, yep. All right, and here's our board. Okay, it's got all of the components over here on the left-hand side, and it's got a blank canvas over here on the right where you can move them and place them. Now you'll notice that the parts on the left don't look like the schematic. They kind of look like the physical devices. They are the outlines of the devices, and the green circles are where those holes are going to be. Okay, so I'm going to go ahead and type move. I could also click right here, the move button, and I'm going to go ahead and take, let's see, the first one of these. Okay, zoom in here. This is J2. J2 is our output. So we'll put it on the right. I'm trying to do this with a lot of things in my way here. So I'll put it over here on the right. We'll just go all the way over to the right for right now. We'll bring these in closer in a minute. Okay. I know, let me, here, it'll freak people out that I'm going off the edge there. It doesn't matter. So I've got that one on one side. This is fine. I've got this one on the other side. I've got the battery. And I'm going to go ahead and put the battery right here in the middle, but I'm going to put it on the back. So I want it on the back of the board, because I'm going to mount it on the back of the board. So I'm going to middle click, and you'll see it just reversed it. Okay. And now I'm going to, let's go ahead and move that a little bit over to kind of get it close to where this is. My other components here are my relay. So let's move this over here. And now I've got my transistor. I'll rotate it. I'll zoom in a little bit. I'll rotate it. Let me turn off my camera. I don't think it's helping either one of us to have that camera on. There you go. All right, so I'll place my transistor right here. I need a diode, maybe right here. My resistor right there. My other resistor right there. Okay. Yeah, it's probably fine. We'll move this down a little. And move this down a little. Now I can move this back over. All right. So here's my basic layout for the board, right? Let me zoom in, kind of show you this. This has got an input jack on the left. It's got the output jack on the right. So I'm going to be able to plug one end into one side of the board, the other end in the other. So the input into one side, the output into the other, and the other components will sit between them. Now I can move these around and get them exactly the way that I want. But I think they're pretty close. I'm going to move this over just a touch. And now the only other thing I will do is I'm going to move this wall so that, I'll show you, zoomed in a little more here. I kind of want it to line up right there, okay? And the reason is I actually want this jack to hang over the side a little bit. I'll grab this corner. And do the same thing here. And these are close enough. I could have done that more gracefully. I don't usually work with the corners. If you grab these in the middle, they will move the entire side. I managed to not do that. So I'm trying to get these straight again. In fact, you know what? I don't like the fact that they're not straight. So I'm going to undo those and do these again. So I'll grab them from here, bring it in here, bring it in. Sorry, it was kind of irritating me there. And bring this up a notch. All right. So that's a good board right there. Okay. Any questions on this yet? I don't see any yet. Even Brady is being quiet, which is good. All right. So a couple things to think about on this. What is it really going to look like? There's a great tool over here on the right that says manufacturing. If you click on it, it will actually show you what the PCB is going to look like. Okay. So here you can see it's got the places for you to put the resistors, put your transistor, to put your relay, put your diode, put your jacks, and then on the back side, it's just got a place for you to put your battery. Okay. Hopefully that's clear. But this is the board we're going to try and make. The last step here is to get rid of all the air wires. And this is a pretty simple board. It won't take us long to do. When I talk about air wires, I'm talking about these thin lines right here. Okay? These lines right here mean that according to your schematic, there should be a connection from this pin, or from this hole to this hole, from this pin to this pin. Okay? So you need to put one there. You need to put one there and choose where those traces are going to go. So let's go ahead and start on one side and get these done. Brady says, will through-hole solder interfere with the battery holder? No. And I should have talked through that on the placement. So if you look, this is, let's take a look at, let's look at it this way again. So here's the battery holder is going to sit right here on the back. There will be solder points underneath it, but that should be okay. We just have to put on the battery holder last. Okay, so we'll solder everything else on first, and then we'll place the battery holder right here, and then on the front side, right here, we will do these two last. This pin and this pin will be the last two things we'll solder, so it will cover the through-hole solders, but it will not interfere. Okay? Hopefully that's clear. Good question. Thank you, Brady. All right. So let's go ahead and route this. To route this, shockingly, you use the route tool. Type in R-O-U-T-E, route. And now you're going to go ahead and draw lines between all of these points on the board. Couple things. Make sure your width is wide enough. 6 is the minimum. On a board like this, I'm going to do everything at 12. This is the width of the trace. The wider the trace, the easier it is for it to flow current. Probably is fine at any of these sizes, but just a good habit to start large and shrink when you have to. And then I'll click here, and you'll see I can just run a line from there to there. It made a little ding sound. The air wire disappeared. And you can actually look in here and see that on this connection, it's telling me, okay, this connection is the JW sleeve connection, right? You'll also see that it's in red. The reason it's in red is because that's the top layer. If you look here, you'll see top and bottom are here. If you have the more expensive version of Eagle, you can do up to 16-layer boards. Lots of people do 4-layer boards, where the 2 middle layers generally just carry positive or the ground and the VCC. But in our case, 2 layers is more than adequate. Okay, so That's one. What's the next thing we need to get? We've got the ring in the sleeve. Let's see down here, where does our tip go? All right, so our tip's going to go over here. Now, you'll notice that as I move around, Eagle is not letting me put it where it's going to interfere with other things, okay? That's a setting. You can turn it off. Well, I don't know why you'd ever turn it off. But, you know, I can go here and run it right over like that, okay? There are probably some great tips that people can share in terms of running top left to right and bottom top to bottom, but I'm not going to worry about those. I'm going to simply route, okay? So these are done. I need to connect from this pin to this pin, and you'll see I have a problem. If I try to connect from this pin to this pin, I can't. It's not letting me because on this layer, on the top layer, there's already a route there, okay? So I hit escape. In this case, I want to be on the bottom, so I can do a drop down and say go to the bottom. Or if I just right click, I will switch from top to bottom. By the way, that little tip right there is huge. The middle click if I said right click, I meant middle click. Middle click changes what layer you're on. So I'm going to run this one on the bottom from here to there. It's nice and easy. I'm going to go ahead and run this one. Let's see, from here to here. Okay. I'll run from here to there. I'll switch to the top, run from here to here, and there to there. Okay. So we're about half done routing this at this point. This guy needs to go here, so let's do that. Okay. This goes to there. I need to go from the tip and sleeve. So this guy needs to go up there. So I can either run on the top like this, it'll go around that hole, that's fine. And then this guy needs to go right here, and this guy needs to go right there, okay? Now, that took a couple minutes, and this board is fully routed. This board is ready to send off and get printed, with the exception of a couple things we'll want to do. But all the routing is done. So at this point, what you'd do is you'd run a check. There's a tool here called DRC. It's a design rule check. It will make sure your board doesn't have any problems. Turns out this one will have a couple problems. Okay. This tells you anything that's wrong. Let me go ahead and just real quickly delete something to show you how to do that. I'm going to type in rip up. If I rip up, let's say, this connection right here, okay, you'll see I still have an air wire. If I run that DRC check again, it will tell me I have an air wire. It'll say you're missing one connection. If I double click, it'll show me exactly where the problem is. I'll go in and route from here. Oh, I got to close this window, sorry. Close the window, route from here to there. Okay. And now my DRC is going to run again. It does have some errors. The errors are not meaningful for us. I'll explain to you what they are. The part that we're using has holes here which are just meant for placement. They're just meant for the pegs to hold it in place. It doesn't actually hold any current. So it doesn't matter that they're too close. I think that somebody could actually fix the part to get rid of that problem. But in our case, we can just approve them. We can approve those errors. They're not an issue. And they're now approved and they won't show up again. So that's our basic board. There are a few things we should really change. And let's talk over them. Let me see if there's a... is there a spell check for any you miss? I think what you're talking about is the DRC I just showed, which kind of is a spell check for did I miss any air wires. It doesn't actually check your spelling. And there are some things in here that I should do before I make it done. One is I should round these corners. To do that, there's a tool called miter. You go through basically and say I want to put a 25 mil rounding on every corner. This is stuff you do absolutely last, because if you ever have to change the layout after you've done mitering and stuff, it just kind of sucks. I should add text on here explaining what all of these things are. I should add some placement notes. I should add our brand information and stuff like that. But as it is, you could absolutely send this to PCBWay or Fab Lab or any of the other PCB board houses out there, and they will be able to make it for you. So here's the front and back. If you look carefully, I don't know why it always moves that. You can see in here where it is putting these traces. You can see any place where we have a via. I probably should explain. I didn't use any vias in this design, which is good, but it doesn't show you how to do it. So let's go ahead and make one artificially. Let's say that, oh sure, let's get rid of this one. So sometimes you need to go across multiple things, right? So you've got to go over a blue and under a red kind of thing. So over a top and under a bottom. So if I was trying to route from here to here, right? It turns out I can do that. Not sure why it's letting me go over all this stuff. It is walk around obstacles, right? Huh. Oh, it's not on route. Hold on a second. So if I wanted to go, for example, underneath this one, anywhere along my path, if I right-click, it will drop a little hole to switch from the top to the bottom layer. And then I can go, this is a really bad idea what I'm doing here, by the way. If I need to go back to the other side, I can do that. Okay? So all of these are really bad ideas for what I'm trying to do. But you can switch from the top to the bottom layer by introducing holes to go all the way through. Now, I'm not going to do that. I'm very happy with how I routed it the first time. But I thought it was important for you guys to see how to add a via if you need it. Okay. At this point, how would you go about getting this made? That's probably the next important thing to show. But I do want to wait and make sure everybody's kind of followed this, kind of has a clue of what it is we're trying to accomplish and how we're going to do it. Let me go ahead and see on Facebook because I haven't been watching it. Hold on. No, we're all good. Okay. So, looking good here. Good. So the next step here is to actually make this with PCBWay. Okay. Well, I don't care who you're making your boards with. I guess I do because I get along with them and they've done a good job, right? But no matter who you send your boards to, you basically are going to follow the same process. You need to take this file, right, this board file, which we should save, and convert it into a set of instructions that their machines are going to follow in order to make the PCB itself, okay? If you look here under manufacturing, there's a lot of information that's really, really helpful. It will tell you the size of your board. It'll tell you what are the components. It'll help you build a BOM, a bill of materials. It'll tell you what drills you're going to need. These are all things that if you're doing it yourself, these are very useful. But the most important thing for getting these made is right here where it says CAM. And when you click there, it will actually create all of the different instructions necessary for them to make the boards. So, for example, right here, you can see this is where the top copper traces need to be placed. This is where the bottom copper needs to be. This is what they're actually going to cut using the router on their machine. Here's where solder mask needs to go on the top. There's where it goes on the bottom. That's where the paste goes. We're not using any paste because we're not placing anything, so we're not doing that. And then this is where the silk screen, that's the text, goes. So these are all the instructions step by step of how to make exactly this board goes. We are going to use what's called Gerber RS274X. Okay, this is the standard. It's just not the. I know it's not the X2. It's the other one. And if you go through here and hit Process Job and say, let's say Switch Isolator Demo. Okay. Whoops. Oh, this one's fine. Okay. It actually, and put it up here. It'll actually create for you all of the instructions for how to make this. So here's all of the different instructions. In fact, one of the things it'll do that I should have done is it'll actually tell you to put it into a zip file right here. Export as a zip, and do that again. There you go, live demo. And so then this file right here is what you need to send to PCBWay, OshPark, wherever else you want to get your stuff made. There's some nuances to that, but they will correct you if you get it wrong. Okay. So this live demo zip file is what you would need. Do you guys want me to go ahead and finish this and go through PCB? We're almost out of time, but I think I can actually go ahead and get a quote of this. I think it might be worth doing to kind of show you the process. I'm going to take that as a yes. So let's go ahead and let's get a new window. We'll go to PCBWay. All right, here's PCBWay. I'll sign in. All right, so I want to get a quote. It's going to ask me a bunch of information on here. The first is how many different designs? 1. The second is the size in millimeters of the board. Well, it just told me that. So if you look here under manufacturing, board, it is 76 by 16. We'll round up. So 76 by 16. Let's say I want to get 10 of them. It's a 2-layer board, normal materials. These are different things that you might want to get. How thick the board is, how much copper to put on it. These are fine. Yeah, there's absolutely nothing fancy here. Green is the cheapest. If you go to any other color, they will charge you more money. The white silk screen is fine. I don't need gold fingers. So this is a lead finish. It's basically just solder. If I want to immerse it in gold, I can do that. But this is a prototype. It just doesn't matter. It says tick yes, which means you accept that you. This really means is if they'd rather do it lead free, you're okay with that at no charge, and we're fine with that. Tinted vias are fine. 1 ounce copper is fine. And we're good. We're not going to order a stencil for this because it's through-hole stuff. We're not going to pay them to assemble it. We'll do that in a future video, and we'll hit calculate. Okay. So it tells us it's going to take about 2 to 3 days to build it. They're going to ship it DHL. It's going to cost us a total of $5 for the board, $21 to ship it, and we're going to have it in 3 days or 4, something like that. For about $26 for 10 of them. So it's going to cost us $2.60 a piece. And if you're going to make more than one of these, you should just do this, okay? So, okay, this is great. Let's go ahead and add this to the cart. it now tells you you have to upload a file, and that file is the one we just created, the Gerber files. So we'll add a Gerber file here, and it lives in here on the Isolator live demo. There it is. These are Gerber files. It takes about an hour for them to review. And that's it. They will send me an email when they've reviewed those files, and if there's any questions about it, if I want it, I will say go, and they will make it. And the kind of freaky thing is, like, I did this on a Monday night, and I got them here on Friday, and it was $26. It's kind of crazy. In fact, I think they have a $5 off your first order. It might be $21 if you guys do it. So what you'll get back from this is you'll get back the board. Let's take a look at what they look like when they come back. So here's one that I had them make recently. You'll see it's just got solder on the pads. It doesn't have gold plating because I didn't pay for it. You can see the traces that they make. This is the silk screen, the text. It's very readable. Both sides are here. You know, they've drilled the holes correctly. Everything is always lined up. And you'll be ready to pop the components on, solder it up, and be done. So I think it's something worth knowing about, right? I think this is something that's worth us taking a look at. If we're going to do more than 5 of something, more than 1 of something, and they're not custom, they're something that are repeatable and usable, I think this is a process we should know about. Now, whether or not this particular tool, whether or not this isolator is really necessary, folks like Julie Marzano could tell us that, right? She could say how many times she needs to isolate. Didn't go off, sorry. How many times she needs to isolate a device from a switch. And if there's a need, we can make one. And if there's not, we haven't wasted that much time. I mean, this was an hour. I talked my way through it, and the rest of it's $26. We can afford that. We can do that, right? Probably the very last thing to show you guys. I just realized I didn't show you. We're not going to go through the full process here. Which one is these? This one. This is our demo. The last thing to show is this little tab here that says, that says Fusion Sync. Now, what this does basically is it will create a design in general AT Maker stuff is fine. It's fine. It will create a design inside of Fusion, which is the CAM tool we use for 3D printing. It'll create a design that will let us create a housing, a case around this very easily, okay? So when this is done, pushing it to Fusion, and it takes a minute, we will then have a board that we can very easily decide, oh, maybe I want to add a hole to it so I can mount it. We should have added holes for mounting it more easily. But we can then say, this is what the case is going to look like, and use that as one of the starting points for the case in Fusion. I would bet more people have used Fusion than Eagle. Chris Young says, OshPark allows you to upload Eagle files directly without exporting. Excellent. It's good to know. Should we make a proc switch that operates without the isolator? Should we make a proximity switch, I assume, that operates without the isolator? Well, we could. It would basically so what you're suggesting is have a proximity switch that also has a relay. I have made a prototype of that. The magnetic field of the relay, if it's too close to the proximity switch, actually caused me some pain. So, all right, I'm not entirely sure why this is taking so long to push this Oh, it's been, I'm sorry, there's actually a note over here that said it was done. So that actually will create a file that we can work with. But yeah, I mean, can we create a proximity switch? Sure, we can create a proximity switch. That's not, it's not a challenge. One with a built-in relay might be a challenge because for me, it triggered the proximity sensor when I used it. So here is a version that I exported before of the Switch Isolator when I did it, just so you guys can kind of see what this will look like. On one side, it's got the battery holder. On the other side, it's got the jacks, the relay, and then the resistors and stuff. And this one, I actually did add the holes for mounting it. And then I created basically a case that goes around it, okay? So we could make something where the plug goes in one side, plug goes in the other side. And we can put AT makers on the side and all. This is a totally different discussion about how to use Fusion. But it is really nice that it took this PCB component and dropped it straight in, so I have exactly the right size that I'm working with, okay? So I think that's everything I wanted to show. I think the next one that I want to walk through will actually talk about making an adapter. I'm going to make an adapter that probably will be a wing, a feather wing, and I think, I'm not sure. You guys can tell me if you have specific things you want me to cover in this series. The third thing, I will go through adding assembly, adding how to have the folks who make the PCBs also get the parts, solder them in place, and basically make like the equivalent of the relay wing that we made that is fully assembled. So we'll do that in the third one. The second one, I got a couple ideas for what to do on it, but if there's something specific you want me to cover, make sure you let me know. I think we're good. Brady says it's like Snake Game. Yes, it's like Snake Game. In fact, it's a lot of fun. It's kind of, I know that's a real geek thing to say, but it's kind of a puzzle. You got to figure out the best way to lay out the board. You got to figure out how to get through the clusters and things like that. And yeah, I do really enjoy the routing part of making PCBs. I spent a lot of hours that I could have been doing something more productive making PCB boards. So, and enjoyed them. So, any last minute questions before I shut down? I don't see any here. Let me see. Can't get to the other screen. Sorry. I don't see anything on the Facebook side. I can't even get to the Facebook side anymore. I don't know where it went. All right. If you guys have any questions, let me know. I'm going to sign out. And I look forward to the next one of these. And see you later. Bye.